Hello and welcome back to chapter 14 of Calculus 3. Line integrals. So far, you learned integration at every level of calculus. Calc 1, single integrals, Calc 3, double and triple integrals, and then in different coordinates as well. In Calc 2, you did the rotation, you did the length of the line, right? Then you also did the improper integrals in Calc 2, where it had infinities in the limits. So a lot of different stuff was computed with these integrals. And all of them were giving you the length, the area, the volume, or bulk, right, 4D. So now we are going to talk about the line integral. And the name is a little bit misleading because the line integral still computes the area, but it's called the line integral. So at least, you know, it's my personal pet peeve. I don't like the name, so I have to state that. So what is happening now? You see, your space before to calculate areas on surfaces was always flat. So in Calculus 1, you had a function that was on the xy plane, and then you did the integral of f of x dx between x1 and x2, but the xy plane was flat, and you were looking for the area under the curve. When we moved to Calculus 3, you had a double integral with nothing inside, and that was again on the flat surface. What I need you to imagine today is a curtain. If you don't have curtains in a house on the windows because of the blinds, you might have a curtain, the shower curtain, okay? You know how it waves, right? Imagine that your shower curtain is made out of some crazy metal material or whatever, and you can flatten that. How do you calculate the area of it, right? So, sure, if you have a curtain, you will hopefully, right, the IQ kicks in, you take the curtain off, you lay it flat, it's a rectangle at that point, I hope, right? And then you measure the rectangle and you know the area. But as I said, imagine that it's made, you know what, made it out of glass. You can't flatten it, right? If it's made out of metal, you take the hammer, you bang it out, and you flatten it, right? It's fine. Made it out of glass, so you can't do even that. So how do you find the area of that surface, the wavy surface? So you see that this is actually a third-dimensional object, right? The surface of it is third-dimensional, but we are looking for the area of that surface. And that's what line integral is for. So what I'm going to do, I'll try to draw this thing, but, you know. So here I have the bottom of the curtain. And then the top of the curtain, right? And the curtain goes this way down. And this line on top is the part of your fxy. The line on the bottom I'm going to call a curve C. All right. And then over here is the area of the curtain, which will be given by the integral over the curve C of f, now ds, and what is this ds? ds is the parameterization of the curve C. So I have that x is equal to x of s, comma, y is y of s, and z is equal to 0 because that's the floor. So to find this C, you have to shine the light on top of the curtain, and it's going to create a single line on the xy plane. You will need parameterization for that in order to calculate the integral. So curtain C, this whole thing is in between A and B, right? So parameter, right? Because the curtain is finite. Otherwise, if it was infinite, it would have infinite area and no need for us to compute anything, right? We know the answer. So we will say that the parameter S has to start somewhere and end somewhere to give us the finite curtain. Now, the top of the curtain doesn't have to be flat, right? That depends on the F that it's in there. I could actually have both ends of the curtain to be interesting, all right? In which case we are going to subtract them, just like area between two curves, right? So the top and the bottom of the curve. Now the only thing that I care about is parameterization C. You see that my integral over there doesn't have limits x1, x2. It just has this C on the bottom. And that's the way, that's the thing that gives away that this is a line integral. You will have that C. You had the double integral with R, region R, triple integral in region D, and now you're having the single integral with C, and that's what represents the line integrals. The derivation for the integral is going to be pretty much the same as our progression through calculus. You make those partitions and then you make them smaller and smaller and smaller and smaller and smaller, and then they eventually go to infinitely thin, infinitely many of them. They all add up to the exact area that you need. So the first definition is the definition of the scalar line integral in a plane, but we are not using this to compute anything. We've seen these concepts before. We use them to explain the concept, and then we have a much more user-friendly version to compute things. So this is the official definition. Obviously, honors by option will have to know this definition to state it. Again, there will be no calculations with this one for either, right? Part of the class, because we have the version for computing. I'll write it later. So suppose that the scalar valued function f suppose that the scalar valued function f is defined on the smooth curve C, which is parametricized by your good old vector valued function R, which is given by x of s, y of s. We are using the arc length parameterization here, parametricized by the R length s. the line integral of f over c is, and now we have the definition. This is the, the Riemann sum stuff. So we have f, use the parameter there. ds is going to be the limit delta goes to 0, summation k starts from 1 to n, and then we have f of x of sk star comma y s k. There we go. Delta sk. So again, this is the definition. Those of you interested, obviously, will look into it. It is the same stuff that we had in Calculus 1 when we described the basics of approximation and then Riemann integral in first two sections of Calc 1. So look up 5.1 and 5.2 first. If you are trying to understand this, first look up the ideas and proofs in 5.1 and 5.2, and then try to connect what you see there to this. Now, I am going to go now for the theorem, which is the one that we use to compute, and this is the one that you must memorize in order to operate in this section and beyond. So, theorem, evaluating scalar line integrals in R2. So, our integral over the smooth curved C of Fs is going to be a to b of f expressed as parameterization x of t, y of t times the vector r prime times of t dt. And if you want the full expanded version of this, then you just write this as the square root. So let's see. Now, why is it multiplied by r prime? Why is it multiplied by r prime?
Because that's ds.
Yes. So we are converting our r length parameterization from the definition that we have into parameterization to parameter t, and that's the conversion factor between the two worlds. So that's why we are multiplying by that. So when you do derivation, you jump from one parameterization in terms of arc length into this one, and we did this before. If you remember your curvature calculations, right? Curvature was expressed and explained in terms of the arc length parameterization, and we had that little trick that we used to transform the arc length parameterization into the parameterization by parameter t, which you can understand this time if you want to, progression to time. So I don't think they gave the transformation in the book. Maybe they did, maybe they didn't. But if you are interested in it, you just go back to curvature section and just look at the 3 lines or 2 lines that they have over there, and you will connect. You will do the conversion the same way. So that's that part. Now, when you are computing this, you will have some function that will be given in terms of x's and y's. Let's say you have x cosine y, all right? So you have x cosine y. Now you have to replace that x in terms of parameter t, replace y in terms of parameter t, plug that in, then you have this to compute, put that in. The t is going to be going from 0 to 1 or 0 to 3 or 3 to 7. Those are these guys, right? And then you will be able to compute the line integral. Where do I get this stuff for t? Well, the shadow of the curtain, that line on the domain xy is given to you. And that is the parameterization that gives you r, which gives you r prime, which gives you everything that you need. Remember that the r, right? The good old r from 3 chapters ago, that good old r is the parameterization of the curve C. That r is x of t, y of t, in case of 3, right, z of t, and so on. So let's take a look at one of the examples. So we have the average temperature. I'll do some from the homework. We can start here. So average temperature. So the temperature on the circular plate R. There you go. They're giving you R, where x and a y is such that we have a unit disk in this case. And the temperature dxy, well, we will be integrating this thing, is 100 x squared plus 2y squared. So confirm that the average temperature computer. Okay, so we are going to take out. So we just want to compute the average temperature now. So now, if you are looking at the parameterization for C, right? I hate writing step 1, step 2, step 3. We're not learning how to tap dance here. But the first order of business is to parametricize the curve. And the curve is the circle. So we should know the parametrization for the circle at the end. So our circle, maybe I should, let me use a different color for this. So how about dark green? So parameterization. So throughout the years, students generally don't have issue with remembering the formula. Usual hiccup is I can't parametricize, which is Calc 2, and then there's nothing I can do because you just didn't learn it. So practice parametrization for a considerable amount of time, and the rest of the section will be a joke. If you don't know how to parametricize, this section is a wrap right away because you just can't make that stuff up. So what do I have? I have a circle. We know that the circle would be parametricized through the set of polar equations, right? And we know that the polar equation parametrization is x equals r cosine theta. Well, we'll use t in this case. and y equal r sine t. But this is a unit disk. We have unit disk. And if I have unit disk, that implies that r is equal to 1. Plug in. So now my parameterization evolved to the point where x is equal to just cosine t and y is equal to just sine t, because r is equal to 1 in both of those equations. So now that gives me the parameterization for this problem. R as a vector in terms of t is cosine t comma sine t, and from there I can find the r prime of t, which I'm going to eventually need. Derivative of cosine is negative sine t, and derivative of sine t is cosine t. So I will need that, because I need to compute the well, what the hell, let's compute the magnitude right now. So the magnitude of this is going to be the square root of negative sine t squared plus cosine t squared, and the whole thing is 1. Okay, so this is the part on parameterization. If you are asking me to explicitly state what was the goal of parameterization, goal is to obtain this. Because this contains what x is equal to, what y is equal to, and it also contains those things as a vector, so that we can find r prime, so that we can find the magnitude of r prime, which is the part that came from conversion that we need for the formula. So the goal of parameterization is to find this r. And sometimes in a problem, r is given, and sometimes it's not. It's given as this unit disk. And then good luck, right? It could be unit ellipse. Oh, not unit ellipse, sorry, just ellipse, right? So then you would have the minor radius and the major radius, right? You plug those in, and all kinds of different things can pop up in these problems. So we'll try to be civil, obviously, but still. So we are looking for whatever I circled in black over there. I'm going to remove it now, but that is the goal of parameterization. Once I have that, the rest of the problem is walk in a park. I am parametricizing a circle, and I want to go to full circle. So I know that my t is actually theta. So in this particular example, t is going from 0 to 2 pi, because this was a polar parametrization. I did not use r and theta. I used t instead of theta. But we still should know that we are parametricizing. So I'm going to, as a part of parametrization, add that t is between 0 and 2 pi. So now I know that my integral c, now f was, which is t in this particular, capital T is for temperature, is given as 100 x squared plus 2y squared, right, ds. I am going to now transform this into the line integral. Integral 0 to 2 pi, 100. Instead of x squared, I have to put cosine squared t. Plus 2 times, instead of y squared, I have to put sine squared t. So this is my function. In a definition is f of xy, and over here is t of xy. My function is now converted from x's and y's into parameter t using the parametrization stuff that we got. Times 1, which is our r prime, magnitude, and then times dt. And now we need to integrate this. 100 times 1 is 100. Kick that in front of the integral. We have to integrate cosine squared. We have to integrate sine squared. And we know how we integrate these things, I hope. Power reducing. There's no other way. So if you do not know from your Calc 2 and pre-Calc 2 power reducing formula, you are doomed in this particular example. So we have 0 to 2 pi. Cosine is 1 plus cosine 2t over 2. Plus, and sine will be 1 minus cosine 2t. No over 2 because it cancels with the 2 that is in front. All of these in parentheses, and then we have dt at the end. Now we can actually combine all of this before integrating, so we don't have to work double, triple hard for no reason. Let's do some algebra. I see a 1/2 and I see 1. 1/2 plus 1 in my book is 3/2. Are we bueno on that? Good. And then I see half of cosine 2t minus the whole cosine 2t. So that better be negative 1/2 cosine 2t, everything dt. So again, I see a half of cosine 2t minus the whole cosine of 2t. So half minus 1 is negative 1/2. Good.
On the second line, do cosine 2 plus sine, cosine squared dt plus sine squared 2 equals 1, and then sine 1 plus sine squared 2.
Yeah. Because now we are going to get that by factoring out the half over here, and that makes this 100 into a 50. And you will still have to do, because you will take, okay, so what Sandrine wants me to do is to say, okay, this is 1 sine square plus 1 more sine square. Use one of the two to add to this and make it a 1. So I have 1 plus 1 of these sine. But I will still have to break this one using the formula, because I will still have sine squared. So I'm, in this particular case, I'm not saving on time or anything, because we will have to be here either way. Because the sine squared will remain. We will use 1 sine squared, and the second sine squared will be, we'll have to do it again. So now I'm going to take a half outside and make this 100 into a 50. And I have 3 minus cosine 2t dt, and now we can finally integrate. So this is 50. Integral of 3 is 3t. Integral of cosine is positive sine, so we have a sine of 2t divided by 2 from 0 to 2 pi. Sine is going to die when I plug in 2 pi, and it's going to die when I plug in 0, because at every pi sine is 0. So that all dies, so 6 pi, so this is 50 times 6 pi, and we're getting 300 pi as the average temperature. So it's like 900 something degrees. All right, that's 950. Yes.
If we were to look at this, visualize like in graphics or something, would this be like weather across a certain region?
It would be the temperature distribution along the disk. So that's because our line along which we calculated this, computed this, is the disk. So it's the average temperature at the edge of the disk. That's what it is. Let me see if they have a graphic of this. They do. So your plate is a disc, like a CD, DVD, Blu-ray, whatever you're familiar with, right? And it lays flat on the ground. The function capital T is giving a temperature distribution on the surface of that disk. And we decided to compute the average temperature on the edges of that disk. And that's what the black C is. So now you see that the temperature is hotter over here than here, and then hotter over here, and less hot over there, and then hotter and less, right? So now the average temperature of all of this along the disk, right? Is that. So none of this exists, okay? This stuff does not exist. All there is a hot disk on the surface, but it's not uniformly hot, right? If I have a disk like this, whenever I'm touching my fingers, that's when it's hot, and over here is not hot, or less hot. But we can represent that nicely this way. So this is more heat, less heat on these sides. It's just a visual representation of what's happening on the surface of this disk. And we are only interested in the red line because we draw the line C over here, and it actually, what it gives us the area of the gray over here. So integral gives us the average temperature. Does it make sense? So none of this exists, right? This is our mental construct to graphically show hotter and colder regions of the flat disk. That's because, again, this disk is two-dimensional, right? It's two-dimensional disk. So when you add another dimension to it, which is a temperature, right? You are not adding a dimension. It's like a sparkle dimension. You're not adding Z. You're adding a concept, right? So that's that part. Good. Let me find another example in homework, and then we are going to take a look at the 3D calculations. So the line integral in 3D. So one more example. Now this one is worked out in a book, and I'm actually happy that I did it because of the question. So we had the visual ready for it. Load faster. And knowing what I do in Calc 3 for years, I should be now just working out few examples of parameterization rather than doing any of this integral stuff, because that's pretty much all of your deficiency. Not able to parametricize. It was either done haphazard in your Calc 2 at the end, or not done at all, and then it was like, it was one section, who cares? there is no chapter 14 for you at all if you can't parametricize. That's the end of the story right there. Trying to get to homework on page whatever. Hey. All right. So I will not be computing any integrals. I'm going to parametricize, set up the integral, move to the next problem. I'll do 2 problems with the stuff that is new, and you better be able to do Calc 1 integral, because once this integral is put together, it's just integral 8b of some function dt. That's Calc 1 integral. And if you can't solve that, then yeah, I'm sorry. So let's take a look at 2. The first problem is going to be a line segment. Line segment is a part of a line. Lines are infinitely long. And if you're using line segment, then you are just chopping off one portion of the line. So problem 16 is asking you to compute the line integral of x squared plus y squared ds on the C, which is the line segment from 0, 0 to 5, 5. I'll keep my color coding, but I'm going to now call it a parameterization. So what do I have here? Well, I have a linear line, and this linear line, I can find the formula for linear line. So we have linear line, and you can go, if you don't know how to find quickly a formula for linear line, go ahead, use formula for slope y2 minus y1 divided by x2, x1, and all that stuff. What I see here, quickly, 0, 0, and 5, 5. That's what I see. So I see that my b is equal to 0, which is a y-intercept, and I see the slope is 1, because it goes 0, 0, 5, 5. So slope is 1. So I am able to write the equation immediately as just y equals x. That's it. Because slope is 1, so you get 1x plus b 0, so 1x plus 0. Now, I have to parametricize this, and one of the tricks to parametricize is to set one of the variables equal to t. So we start with x equals to t, but because x is equal to y, then also y is equal to t. And if you are looking at this, right, this is infinite. This is infinite. But you will restrict your t between 0 and 5, so the lowest value t can take on is 0, which creates 0.00. The highest value it can take is 0.5, which reaches up to 5, 5, and it picks up everything in between. So this is parameterization for a straight line between 0, 0 and 5, 5. Now, this gives me my r. My r of t, vector, right, is dt. And my r prime is 1, 1. And my r prime magnitude is root 2. So now that I'm done with parameterization and I have all of the other bells and whistles I need to put the integral together, integral over curve C of x squared plus y squared ds is going to be integral from 0 to 5. That comes from the parameterization piece, which, right, so we have 0 to 5. Now x squared, so that's t squared plus another t squared times square root of 2 dt. So one more time, your x is equal to t, your y is equal to t, so x equals to t squared, y equals to t squared again, r prime is the root 2, and you have this. So that's 2t squared, kick out 2 root 2, integrate t squared, plug in the limits, and you are done. So here you get the Nike symbol over here, and you know what that means when you review your notes. So do that part. Let's take a look at some other parameterization. Problem 18 has y equals x squared. All right, so let's take a look at that one. We are supposed to integrate the line integral of cube root of xy ds, where c is the curve y equals x squared, and x goes from 0 to 1. Okay, parameterization first. So we will set x to be t, and then y becomes t squared, and because x equals to t, direct translation 0 less than t less than 1. This is the cheapest and the fastest way to do parameterization, and it's amazing when it works. Can't do it for a circle, but you can do it for most of these basic functions. So setting x equals to t, and then replacing every x of the original equation with t, you get the formula for y. So immediately I have that my vector r of t is tt squared, and then r prime of t is 1 and then 2t, and now the magnitude of that is going to be the square root of 1 plus 4t squared. I have all of the building blocks to put my integral together. So the integral over curve C of the cube root of xy ds is equal to the integral. Again, wherever you did the parameterization, you need to have this part that limits your t values. So that's going to be 0 to 1. Cube root of, instead of x, I have to put t. Instead of y, I have to put t squared. Oh, how convenient, huh? Times another square root of 1 plus 4t squared dt. And I just hope that you will be able to quickly integrate this without thinking too much. Which method of integration takes care of this problem? U sub, very good. The stuff under the cube root is t cubed. Cube and cube root cancel. And when they cancel, you just get a t in front of the square root. Use a u sub on 1 plus 4t squared. Fix the coefficient of 8 and you're done. They have all of this explained in a procedure, right, boxed off on page 1063 of your textbook. Now, so just There we go. Solve that. Now we are moving on to theorem 14.2, evaluating scalar line integrals in R3. Just writing the formula, everything is the same. So evaluating scalar line integrals in R3, which is 3D. So our integral of the FDS is equal to the integral a to b, and now you have your f in terms of x of t, y of t, z of t, everything multiplied by r prime of t, which is a vector, and times dt at the end. So same calculations. Number 1, parameterization. Number 2, put the integral together. And number 3, integrate. So doesn't matter what dimension you have. Right? This can be done in any dimension because it's just the amount of vectors that, amount of dimensions you have, and you just stuff them in a vector. So this can be generalized to any dimension. Now, whether or not it has a purpose, right? That's a different story, but next part of the same lecture is line integral of a vector field. So we'll start with the definition. Try to understand this later. So let F be a vector field that is continuous containing the smooth curve smooth oriented curve C, parametricized by arc length smooth oriented curve. Let T be the unit tangent vector at each point of C consistent with the orientation. The line integral of f over C is integral C f dot t ds. What is it computing? You know how you get inches of rain? Does it even make sense to have inches of rain? It shouldn't, right? But we understand it. So what am I going to do? I'm going to create a smooth curve on the floor. Maybe a circle, right? Take a piece of chalk and draw a circle. I know how to parametricize that, right? Fine. Oriented. Why is it oriented? You remember that every parameterization has oriented because your t time progresses from 0 to positive numbers. So when you parametricize circle, you get a counterclockwise orientation for circle if you use x with a cosine. If you use x with a sine, orientation goes the other way. It goes clockwise. For the line, which we parametricized earlier, 0, 0 to 5, 5, it was oriented to the right, and up. Because it went from 0, 0 at time equals 0 to 5, 5 at time equals 5, whatever, seconds, minutes, years, whatever. So you have those concepts. And what I want you to know, what am I computing here, right? So I'm going to draw a circle. I could have drawn a line or whatever. I'm going to draw a circle on the floor. And I want to let it rain, right? It's a vector field, right? Would you agree that each one of those droplets is making a vector that it's striking with a force, right? So each one, so there's your vector field. So we have a vector field, we have the smooth curve, and now I'm computing the area of the whole. So technically, I'm getting the average amount of rain that's falling on that line. So I'm going to make a straight line and compute the rain curtain, right? Of how much rain on average I get along that line. So that's what I'm computing. So it's not the same concept. It's not as easy to visualize as if I say you have a curtain that's hanging and just because curtain you touch, right? The curtain you see. But what you don't see in the mechanical engineers, anyone? You have a tunnel, right? And then you have the wind tunnel to test the aerodynamics of the cars and the airplanes and things, right? And you need to know that's a vector field, right? Because it's not solid, right? It's a tunnel, and you're going to push the air through, right? And you can take a look, because every curve of a car or a plane or whatever you are testing in that air, right? That's going to give you C over which you are computing things. So there is a lot of applications of this, but it's not as obvious because you are not dealing with vector fields. You're not dealing with electric field, magnetic field, gravitational field. You live in them, you exist because of them, but there is no interaction where you sit, you move the curtain, you understand that. You touch the things that have volume and mass and things. So yeah, nothing so far was abstract in calculus. It shouldn't have been, right? Because you know about the velocities and all of these kind of things. This stuff is difficult to picture because you have zero experience with these things. So try to read the section and really think of these examples and start thinking about, okay, I have a fan that it's pushing, right, and I have water pressure, I have, right, traffic flow. That was an excellent one on the on a 2D case, and so on. Because yeah, we are two-dimensional with our cars, right? What we did is we paved certain part of the land, and then we took some paint and draw some lines, and everyone is following that stuff. And if you don't, you pay money, right? That's technically. So just think of it as simple as it is, because it is simple. You have a drawing on a surface of the planet, and you're just trying to stay within that drawing. That's what it is. But you're creating a vector function, because every single car on its own is a two-dimensional vector that's pushing forward, and some are faster and some are slower, and then there are functions that can describe that motion. So now, again, as before, this definition over here is just the definition. It's in terms of the arc length. We know we're not computing anything in terms of arc length, so we'll just leave it there, and then we move on to the one that is actually our calculation. Now, when you transform all of this, you have that your vector t, if you remember at all, unit vector t is r prime divided by r prime, right? And then you also have the conversion from ds into dt gives you another r prime. So t is r over r prime, and conversion gives you r prime, so those guys cancel, right? So the whole thing is just the vector field in a cross product with the r prime, because the magnitudes of r prime cancel. So we have our integral r prime over magnitude of r prime times the magnitude of r prime dt. So this is your unit tangent t, and this is your conversion from ds into dt. So these puppies cancel, and you are left with the vector valued function f dotted with just r prime, no absolute values here, just r prime. And this is a simple dot product between two vectors. I don't care if this is a 2D space, 3D space, 8D space, it doesn't matter. So all you need to do is to write it out. So what is the formula that you are going to use to compute these things? It's going to be integral from a to b. Again, it's dt, right? So integral from a to b. And now, remember that your f, vector field f, is fgh. Right? Actually, let me write that before I do this. So your vector f is fgh, and your vector r, well, r prime, is going to be x of t prime, y of t prime, z of t prime. Let me fix the f of t, g of t, h of t. Much better. So now the dot product from above, I'm going to box this one. So your integral in the vector form over here is going to be integral from a to b. And now we do the dot product between the two vectors here. So you have f of t, x prime of t, plus g of t, y prime of t, plus h of t, z prime of t, all of that in parentheses dt. So this is your way to calculate line integral in the vector field. We'll do examples now. So other version of the same thing, shorter version, is to write integral a to b, and then you just write f dx plus g dy plus h dz. Generally, this notation freaks people out. And then the last one, right, vector f dotted with dr. That's also the vector one. The one that I boxed is the one that you are using to compute things. The other ones are there for future definitions and things. So you see your f dx. What is dx? This is dx dt, right? So if you think about it, this over here is dx dt, and this over here is dy dt, and then the z dt, and when you multiply each one by dt, it kills dt, kills dt, kills dt, and you're left with f dx g dy, right? It's just notation, it's manipulation, it's not something that, you know, but you need to know it because it's going to be bad. So what I boxed is what you are going to use to compute your problems, and then underneath is the notation that you must know so you can push further through the class for later on. So now let's take a look at a problem. So I'm going to, I could do a problem from before you lose your mind, what's what? F, G, H, those are the functions from vector field, and vanilla x, y, z of t are parameterization from C, from curve C, okay? And then you take the derivatives to get primes on them. So you can see that here. It's vector field f times dr, right? And r is the one that gives you x, y, and z. That's parameterization part. Now, whether it's 2D, 3D, doesn't matter, right? It's just obviously with 3D more calculations, but it's the same in terms of the procedure. So, let's see. Figure out f dot t ds, where the vector field is y minus x comma x on the path so I want the path quarter circle from 0, 1 to 1, 0. All right. Well, I'm going to draw this circle and say I'm going from 0, 1 this is where I start to 1, 0. Which way do I go? I need a quarter circle, so I go from P to Q, so I have to go this way, right? You see, that is the crucial piece of information, that little arrow there. What do I know about my parameterization that now that that arrow is that way? Clearly this is all ones. What's my parameterization? What's R? Right, so what's my... I know it's XY, right? So what's X? Sine. Nice. Yes. If that arrow was the other way, it would be cosine. So sine t, cosine t. Because arrow clockwise, arrow is clockwise, your x is sine. Arrow is counterclockwise, your x is cosine. Good. All right, we got that. So now all I need to do is to compile the entire integral up there because I have my r. I need r prime, right? So this guy over here is x of t, and this guy over here is the y of t. They get plugged in here. Yeah. All right. So I have my parameterization, and now that I have my parameterization, I will need my r prime. Which is cosine t negative sine t. I'll have to use that as well. And now I just need to put this thing together. So my integral over the smooth curve C, and circle is a smooth curve or quarter circle. I have f dotted with r prime dt. So this is integral from a to b. Ooh, what are my limits on t? You are going counterclockwise. If you were going clockwise, sorry, if you were going counterclockwise, you would have to go pi over 2 to 0, right? But you are going counterclockwise, your world begins at P. And that's where your 0 degrees now is. And it's going to go down to Q, which is pi over 2 away. And that's because the arrow is this way. If the arrow was the other way, and you still had to go from P to Q, yeah, then the limits would be switched, and then you have to switch them, which introduces the minus sign and so on. But we don't have to do that now. All right, what's my F? Well, Y is cosine t, minus x is sine t, comma, x, which is sine t. I need to dot that with r prime, which is cosine t, comma, negative sine t, everything dt. Yay. 0 to 2 pi. And now I need to do the dot product. Dot product is, remember, you multiply each one by, you multiply x components, you multiply y components, and you add them. So I have a cosine squared t minus sine t cosine t plus, for the dot product, and then I have negative sine squared t. Oh yeah, power 2. So minus sine squared t dt. Now this is really going to push your knowledge of trig identities. I'm looking at this and I'm thinking, joke, because I have cosine squared t minus sine squared t minus sine t cosine t dt if I rearrange. These two puppies over here are giving me cosine 2t. That's a trig identity that you learned 2 years ago or earlier. And I don't know if you know it or not. If you don't have to know it, because you can always go ahead and do the power reducing, which you must know. Right? Power reducing is a survival thing. This is just, you know, you're cute if you know it. All right, that's that. And then the second one over here, so minus, and the second one over here is 1/2 of sine 2t. And now all of this dt, integral 0 to pi over 2. So now I have a cosine 2t. Integral of cosine is sine, so I have sine 2t over 2 minus integral of sine is negative cosine, so this turns into a plus. This becomes 1/4 of cosine 2t. And I'll actually write this half in front, so 1/2. Everything computed from 0 to pi over 2. When you plug in pi over 2 and double it, becomes pi. Sine of pi is 0, so that's a 0. Plus, when you plug in pi, cosine of pi is -1, so this is 1/4 times -1. When you plug in 0 over here, it dies, so plus 0. And you plug in 0 here, you get -1/4. So we get -1/2 as the total. So we calculate. Now again, you're going to maybe ask or try to ask, what is the significance of -1/2? Again, this problem had nothing going on. That was important, so there is no significance. It's just we outlined the mathematical procedure to solve the problem. But since you are so insisting on the application of this thing, we put the work integral, obviously, right? Work in the in a field. Everything that we have today depends on this formula. This is what spins the electrical motor. An electrical motor builds everything we have. It runs our factories off of the AC currents. That's Nikola Tesla. Okay? So, you put some electricity in a wire, wire creates magnetic field. And that magnetic field hits the other magnetic field of the rotor. So motor has two parts. There is a static part and the rotational part in the middle. And when they both have magnetic fields, you get a spin. How do you get those magnetic fields there? Electricity in a coiled wire. Electricity in a coiled wire creates magnetic field. So, everything that is produced, everything that you touch, everything that you see, had to have electrical motor at one point in time or all the points in time there, and now we have electric cars coming up and trains and everything else, right? It's all electric. It is a very simple idea. You have a field which is doing the work. And the formula that I'm writing right now is the one that computes all of that stuff. So, the work is integral of C of F dot T ds is equal to A to B, whatever your field is, times R prime of T dt. I didn't write anything new. It's the same formula above, right? I'm just giving it a purpose. And the purpose is technically everything we do. The class is over and I still have 3 concepts to go through in this lecture. Who wants to go home? Yeah, that's a... Yeah, I know. No, people love it so much. We talk about circulation and flux and then we go. Do you want to know that fan over there? What's the circulation? And you want to know what the flux is? Because next time you're in an interview for some engineering thing, they're going to ask you to compute flux like they did ask some people. And it's not going to be pretty. So... circulation is exactly what it says in the title. And we are going to draw pictures to make sure. And then the flux is something that you are not used to. Then the flux is what emerges out of the area as a perpendicular push. And circulation is what is in the plane. So when that blade rotates on the fan, the amount of stuff, which is the wind that it creates, perpendicular to the blade, which you feel, that's flux. But all of the side stuff that goes around as the propeller turns is the circulation. And then you take a look at the different fields, and you will see that for certain fields, like rotational field is going to have maximum circulation and 0 flux, which should make sense, right? So we'll have to continue this because I do have another 30 minutes. This lecture is very long. So I have to go through those two and then examples to compute these things. You will see the pictures. And the formulas that we get in here are going to be extremely important for 14.4. So let's make a part 2 then on Wednesday. So we'll play a little bit of a catch-up game. I'll have to check that. Let me just say bye over here.